So we want to talk about order of an element in a group, leading up to cyclic groups and so on. G is going to be a group throughout. The multiplication operation or the group law is denoted by a dot, and the identity element is denoted by E. And let's start to get a little loose about notation. We'll write, instead of writing A dot B, we'll just write AB, the dot being understood. So fix an element in the group. Then we want to define a to the power n for any n in the integers. First of all, a to the 0 is going to be defined as the identity element. It's like in usual number system. A to the 1 is certainly going to be a. A to the 2 means a times a. A cube means a times a times a, etc. So a to the n inductively means a to the n minus 1 times a. Or if you wish, it means a times a times a n times. Right. That defines a to the n for positive n. So this defines a to the n for non-negative n. These are all elements of the group. And for negative n, like a to the minus 5, if you want to define, you define it as the inverse of a to the 5, which you know exists in a group. And if n is negative, then define a to the n to be the inverse of a to the negative n. You see, if n itself is negative, then negative n is positive. So you already know what this means. Take its inverse, and that's your definition of a to the negative number. Okay, so this defines, so we have all these elements. A to the n for all n in integers. You verify this little lemma. A to the m times a to the n is the usual law of exponentiation. To the m plus n, and a to the m to the n is a to the mn for all mn. For all a in G and all mn in Z, we have the following two things. In particular, if you take n equals minus 1, then the inverse of this guy is a to the minus m. It requires some work, like you're trying to, if m and n are positive, then the first one is visible, but you're also trying to check things like, so one way to check that would be to multiply both sides by a to the minus 2, for example. Then on the left, by associativity, you get a to the minus 5 times a to the minus 5, which is a to the 5 and its inverse multiplied together, so that gives identity. Also on the right hand side, you get a to the minus 2 times a to the 2. This is supposed to be the inverse of that, so they multiply to identity. So these two are the same, but then in a group, you know you can cancel. That was one of the little things we proved, so you get that. So that's roughly how these proofs work. You have to do a little induction or something. I'll leave it as an exercise. Okay. All right. Definition. Say that A in G has finite order if a to the some power is identity. And of course, a to the 0 is going to be identity. I don't mean that. I mean some positive power for some natural number k. Otherwise, we say a has infinite order. And you can verify, here's a little exercise, that a has finite order if and only if exercise. A has finite order if and only if two different powers of a are the same. Order if and only if some a to the k is equal to some other a to the m for two integers k and m that are different. Of course, if a has finite order, then you know that a to the k is a to the 0 for some positive k. So there are two different numbers. And if you do get a to the minus 3 and a to the 5 are the same, then you know by multiplying by a to the 3 that a to the 0 and a to the 8 are the same. So that would tell you that it has finite order. Roughly, that's the idea of the proof. I'll leave that as an exercise again. So if a has finite order, so this is the central definition. I want to define order of an element, I said. So suppose a has finite order. What that means is that when you write these elements in the group, somewhere down the line you see identity. So there will be a first time that you'll see identity. So there will be a smallest n positive for which a to the n would be identity. And that n is called the order of a. So if a in G has finite order, define the order of a denoted by to be the smallest natural number n such that a to the n is identity. And if it has infinite order, meaning there is no such n, then you just write it, the order is infinite. So if a has, so we write if a has order n, we write if a has infinite order, we write. It's just a notation. Okay. To give a little example, maybe take Z mod 9 star. That's one group we considered. And let's take the element 4. Well, we have 4, that's our A. And this is our G. So what is 4 square? 16, which is 7. And then what is, so that's not 1. And And then what is a cube? Well, a cube is 7 times 4, that is 28, which is 1. So that's the identity. So this shows that the order of A is 3. So that's the first time you got the identity. Of course, if a cube is 1, a to the 6 is also going to be a cube times a cube, which is 1 times 1, 1. A to the 9 is also going to be 1. A to the minus 3 is also going to be 1, etc. But I'm going to take the smallest positive number. Okay. On the other hand, if you take the multiplicative group of real numbers, with multiplication and 1, and you again take the same element, then when you take its power, it just goes 16, 64, and keeps growing. It never comes back to identity. These are all distinct. So this guy has infinite order. So there is some abuse of notation. This 4 is not that 4, right? This 4 is the 4 in Z mod 9 star. It's really 4 mod 9. But you know what I mean. Okay. So if you take another example, maybe, I don't know, here is a permutation of 4 letters. This is an element of S4. Let's call that A. What does this do? One way to picture it, to figure out what it does to the 4 letters, 1, 2, 3, 4. It takes 1, 2, 2, 2 to 4, and then 4 back to 1, and it takes 3 to 3. So what would A square do? Let's apply A twice. Then 1 goes to 2 and then goes to 4, so 1 goes to 4. 2 goes to 4 and then to 1, so 2 goes to 1. 3 goes to 3 and then to 3, so 3 goes to 3, and 4 goes to 1 and then to 2, so 4 goes to 2. That's not identity. But when you take the third power, you see that 1 goes to 2 and then 2 goes to 4 when you apply it again, and then 4 goes back to 1 when you apply A again. These are called what are called 3 cycles. And similarly, you'll check that 2 also goes to 2. 3 already went to 3 anyway. 4 goes to 4. So that is identity. So again, this element has order 3. Okay. So like if you take this element, what does this do? This flips 1 and 3, flips 2 and 4. Let's not call it A as well, call it B. This element has order 2, because if you do it twice, B times B, you get identity, etc. Okay. You can check this little lemma. Assume an element in a group has order n. Then some power of it is identity if and only if this k is a multiple of n. Because if it has order n, that means a to the n is identity, so a to the 2n is also identity, a to the 3n is also identity, a to the minus n is also identity. So any multiple of n, power of a is identity. But you can check the converse as well. And in the same vein, two different powers are the same if and only if their difference is divisible by n, which means k is congruent to m mod n. We'll talk a little more about order. Maybe I should mention one thing here. If G is written as an abelian group, and then the identity is denoted by 0, in that situation you don't write A times A. Instead of that, you write A plus A, and you call that 2A instead of calling it A square. And instead of calling it A cube, you call it 3A. And instead of calling it A inverse, you call it minus A. So to get used to that. So there, the order means the smallest n such that n times A is 0.